Hi, everyone. My name is Sarah Parker. I'm here on behalf of Google's video codec team, and I'm going to give an overview of the new experimental tools that we're currently exploring. So after a little bit of background on the project, I'm going to give kind of a high-level technical overview of a lot of the different experiments that we've been working on. Several of these are things that we either plan to do in the future or are a work in progress. So I'm going to give results when they're available, but I won't have results for every single experiment that I present today. So I assume everyone here is familiar with AV1, but this is kind of an update on where it's at right now. It currently gives around 31% BD rate reduction over VP9. It accounts for about 80% of the desktop market, and YouTube uses it as the default on compatible browsers up to 720p. I believe 1080p is kind of in the experimental stage. So given the success of AV1, AOMedia wants to continue to develop new coding tools and hopefully make progress on the next generation codec as AV1 continues to improve. So the first set of tools that I want to talk about are block partitions. Here is an overview of what currently exists in AV1. So you can see there are several different types of block partitions, and the only one that is currently recursive is this four-way square split. So this is kind of the proposed scheme that we want to work on. All of them, we hope to make all of the partitions recursive, and we're also adding these ternary partitions, which replace the four-way horizontal and vertical split, and just merge the two partitions in the center. So with this scheme, you get all of the same partition types as this one here, but it's a lot more flexible. This one is still a work in progress. We've made a lot of progress on adding all of the additional recursion, and we have implemented the ternary partitions, but the results are still pending. The next group of tools that I want to talk about are transform coding tools. So this is currently our new transform partitioning scheme. So for the square and rectangular allow either no split, or for square it's a four-way split, for rectangular it's a two-way split. The bit stream, I think, allows for 2 levels of recursion. But in a lot of our speed features, these are the only ones we're actually enabling because we found that the extra recursion depth doesn't give that much performance gain or much coding gain, but it makes things a bit slower. So instead of focusing on adding more recursion for the new transform partitioning scheme, we're adding different partition types. So these are the ones that are all currently implemented in the experimental branch. They're exactly the same for square and rectangular partitions, or square and rectangular blocks. And this currently gets about 0.6% coding gain, but it's only implemented for interframes. The results for intra are still pending. In addition to the new transform partitions, we're exploring data-driven transforms. In libaom experimental branch, we call these MDTX. And they're transforms that are learned by collecting block data. And the schemes are slightly different for inter and intra blocks, so I'm going to talk about those individually. For inter, we have trained MDTX and flipped MDTX, and we create 2D combinations between those two in DCT. There's a typo on this slide. Instead of 6 additional transform types, it's actually 8 additional transform types. And these are just added on top of the 16 that are currently available in AV1. Intra is slightly different. We have combinations of MDTX and MDTX DCT, and these are going to be mode dependent. So these 3 transforms are added for each intra mode. So this is what's available for intra right now. These ones are the original ones from AV1. They're not mode dependent, and then these 3 are implemented for each mode. And the last thing that we're adding for intra transforms are non-separable mode dependent transforms. So the motivation here is that the intra residual typically doesn't exhibit a pattern that is strictly horizontal or vertical. So non-separable transforms can better capture these patterns. And we're looking to implement 1 2D non-separable transform per mode. So these ones are also mode dependent. This is just an example of what some of them look like. We realize that non-separable transforms do add a bit more complexity. So right now we're constraining this to 8x8, 4x8, and 8x4. But we are exploring doing second-order transforms to try and get some of the gains from non-separable transforms for larger block sizes. These are some of the results that we currently have. There should be two of these, yeah, that we currently have for this experiment. So we don't have to go over each of these categories. I think the main one to look at here, this is for both inter and intra separable and non-separable transforms. So this is currently getting about 0.87% on the mid-res set. We also added a few more intra-coding tools. The first one is an adaptive recursive filtering-based intra prediction. So currently in AV1, we have a recursive filtering intra-prediction scheme where a pixel might be predicted by applying filters to the neighboring pixels that would have already been reconstructed by the decoder. So this is a similar scheme, but it's making it adaptive at the block level. So for each block, we'll use some training region, which isn't strictly 1x1. This could be, say, like 4x4 in depth. And we use this training region to solve this optimization problem and learn the filter coefficients for each block. There are several different filter configurations. This shows, so we have 2, 3, and 4 tap filters. The dots represent where the taps are and the number of taps. And we can train from either the full context, just the left, or just the top. So these 18 filter configurations times the 3 training regions yields 54 modes. That's a lot of modes. So we do have a ranking process that I believe is done offline where we can pick up to, say, 7 of these and only select from those. So we do have a breakdown of results using 7, 5, and 3 adaptive modes. So if you use 7 adaptive modes, the results are a little bit more than 1%. We are also looking into some machine learning entry-based coding. This is currently only implemented for intra. And the idea here is to get the probabilities, we currently use these lookup tables. And the disadvantage of that is that these have to be kept relatively small. And it forces the contexts that are used to index into them to be categorical. So the proposed idea is to replace these tables with neural net or machine learning models. And I believe the ones that we've currently explored have been logistic regression. And we use the top and left neighboring blocks as the input features for the model. And this is currently getting about 0.6% coding gains only on keyframes. A lot of these inter tools are in the preliminary stages, so I'm not going to go into too much depth. But the things that we're thinking of looking at are decoder side motion vector prediction. So this could be either including some sort of motion vector search on the decoder side, or maybe sending only integer precision motion vectors and then getting the subpel precision using various techniques on the decoder side. We're also looking into illumination compensation to help when different frames have changes in illumination. And we're also looking into the ability to send motion vectors at different precisions. The last group of tools that I want to talk about are the Inloop restoration tools. So this is kind of a diagram of the entire coding scheme. And at the end, once a frame is reconstructed, it needs to be restored. AV1 currently uses CDEF and loop restoration to do this. So one of the things that we're currently exploring is replacing CDEF and the loop filter with a CNN. This is still a work in progress, but we're currently getting about 3 to 4% coding gain, but the model complexity is pretty big. And we're continuing to look at how to get the model size down to make this more feasible. And we're also looking into implementing non-separable Wiener filters. So those are all the tools that we're kind of looking at right now. As you can see, we're starting to get modest coding gain, but we're really hoping that people will be interested in helping to help push this forward. Yeah, that's it.
I think it's excellent to see a bunch of new ideas, and some of them already providing games compared with what we have today. On the other hand, have you thought about when is the right time to involve decoder vendors into this analysis? Because they might provide you some guidance on what things make sense from hardware implementation and what things maybe will never happen on a decoder, and maybe you should not look at those. Have you thought about when is the right timing?
I don't know if we have discussed that specifically. A lot of these are like, we've only been working on them for a couple of months. I think that's a good point though, so we don't spend too much time doing things that will never be feasible.
Because my experience is that you might not have that knowledge.
Yeah,
And
I think you're right.
I have seen in the past very, very positive work when those ideas are presented to the hardware manufacturers, and then we give you the guidance and you might work on something very similar.
Yeah.
But the earlier you get that feedback, I think is positive. At the same time, you don't want to be fully constrained that you don't do things. But I have seen in other places people coming with 8,000 entries on the lookup table, and based on that, the feedback, they came down to 4 entries and got similar results.
Yeah.
But they got the feedback early on.
I think there's kind of a trade-off, because I think we want to explore how much gain is possible and then worry about complexity later. But I think you're right. It's good to get that feedback early.
Mm-hmm. Okay.
But here first.
Yeah, I have just a question about what do you mean by data-driven transform? Can you elaborate on that a little bit?
Yeah, so I can do my best. I didn't personally work on this experiment, but I think the idea is that a bunch of block data is collected to get a correlation matrix to get a KLT. But I think the block data in this case is collected from blocks that don't do well with other transform types. And I think that's determined just based on RD. So we're trying to learn transforms that kind of exploit the transform space that isn't getting good results with our current transforms.
The data are those that's pre-coded? Like, it's not, you're not going to send the transform itself, right?
No, those are, yeah, so the training is done offline. So we just send, so I think the actual transform is coded, like hard-coded into the code base.
So it's not like adaptive. So it's just one of the transform that was designed from the data. It's not like online adaptation based on recently coded.
No.
Okay, thank you.
Just a simple question. On the intra-coding tools for the ML, you mentioned it was for the keyframes only. How about for the other tools, the gains? Was it for keyframes or for overall performance?
For all
Yes,
of the tools or the other?
No, I mean, you had intra-coding tools. So one was, you were showing the ML performance only on keyframes. But for the directions, was it keyframes only, or was it, like random access or? Keyframes, okay.
I think keyframes only.
Okay, so good. Do you have also complexity numbers, like especially on the encoder? How much more time do you take to encode? I mean, like roughly?
I don't, I'm sorry.
Expanding on comments from Alberto and Alexis, so if you had a specific hardware block that was proposed by a hardware manufacturer, and instead you looked at what you could do with that hardware block, would that be another way? Like if you could count with a certain CNN engine, what could you do?
Can you repeat that? I'm sorry.
Yes. So if you could count with a certain piece of hardware that was recommended by one or many hardware developers.
Yeah.
Then you could do your research looking into what you could do with that hardware.
Yeah, I think that makes sense. Yeah.
Yeah.
We haven't tried that. Have we tried that? I don't think we've, yeah. A lot of these are very much in the early stages. But
I guess nobody's come to us with a hardware block either yet. So
Okay.
if somebody came to us, maybe we would evaluate it.
Okay.
Actually, let's get the back first.
Do you have like a goal, I mean, internally in the team, like you're looking at what would be a good, something to achieve, like 10% improvement on AV1, I mean, and like a time frame you have in mind, or it's still in the exploration
yeah,
stage?
so our team does have a goal per quarter. I don't know if I'm allowed to share that. I'll err on the side of not sharing that, but we do have specific goals.
Yeah, I can just say that internally we have a goal for improve conversion by 5% per quarter. But as everyone you know, at the Google, we typically shooting for really, really aggressive bar, right? And we don't think that if we're getting anywhere even close, that's a big achievement. So I actually think that we did quite well so far, right? Not hitting the 5% goal, but we got some quite good gains to show here, right?
So one concern I have is Alberto said earlier, we tend to shoot mostly for the decoder. We don't care about encoders, but actually that's not really true. I think it's really important to also care about encoder, especially hardware encoders. So when you're designing, algorithms, and this is, we're trying to look at this also from our perspective. You guys are looking at algorithms, we're also looking at algorithms. I think it's really important to understand that hardware encoders, also have limitations, and only designing for hardware decoders, it's actually wrong. We have to also design for hardware encoder complexity, being able to actually implement whatever algorithms we design also in a friendly way, for our chips, in an encoder, nice way. So I would strongly encourage you, don't only look at gains that you could achieve on a theoretical software encoder, but also try to figure out algorithms that work nicely on encoder designs. You would agree, right? So
yeah, three things: area, low power,
right. Because, we're finding quite often that even happen in AVC and HEVC, encoders don't go as fast. You cannot go and put all the different tricks that people went and designed in HEVC inside a chip. Therefore you get a big compromise in performance. Same thing happens in AV1. If you want to make a very, let's say, elegant and a good encoder for everyone, it's really costly. You cannot implement all the tools. So we have to think of alternatives. How do we also take whatever we design for the decoder and put it also in an efficient hardware design for the encoder? Just keep that in mind. We have to keep our minds open. The world is changing. It's not just decoder design friendly.
Yeah.
Yeah, there were a question about the end goal. I think Google was very nice to tell us that they have a short-term goal, and it's also a way to get there. If you have 5% every quarter, in a few years you will get to the 30-35% goal that the AOM board has been trying to see, and not in this short time frame, because I think one of their realizations is that it's difficult to meet these goals. Technology is getting harder to deliver games compared with what we had in the past. That means I think currently we have a much higher goal than the 20%, but we're also willing to give it a longer time frame, definitely talking years, not quarters, to be able to get there.
I think the one thing to say there is you mentioned the AOM board, but the AOM board haven't got any published goals at this point in time.
Clear guidelines.
There were some internal discussions over what we might be aiming for, but there's nothing that's been published that speaks about coding gains or timeframes. And that's for the reasons that we don't want to kind of, what we talked about at the very beginning, where we don't want to spook the hardware manufacturers. So, yeah.
Yeah, just a couple of more thoughts about the hardware encoder complexity. So, for example, in AV1, we have intra-BC. However, in hardware implementations, we always have that filters pipelined with the rest of the encoding pipe, so it's unusable completely. Another example is this, you mentioned, Sarah, that the smaller transforms, like going recursively to very small transforms, is not usable because it's not it's slowing down the encoder. But in fact, in hardware encoders, we oftentimes don't get the optimal partitioning in place because we cannot do recursion there either. And now that we are not able to go to these small transforms, we actually hurt our quality because we cannot compensate for the wrong decision we made earlier. So these kind of things should be considered. Thank you.
Thank you.
Okay, last question.
Can you explain a little bit about the neural net in Inloop filter? Is it like based on the network, you come up with the optimal set of parameter that will be hard-coded into the spec, or you are looking at a inferencing engine that will dynamically change the filter coefficient per content?
I'm sorry. I think DeBargo. I haven't worked on the neural networks, so I think DeBargo will give a better.
Yeah, it will be hard-coded into the spec. Yeah. I mean, that's what we're looking at as of now. Yeah.
Okay, great. Thank you, Sarah.
Thank you.